So today I'm going to be talking about this particular topic. You may know it by different names. So another way to express these two dimensions is bias and variance, and also underfitting and overfitting. So this is going to be the topic of the next 10, 15 minutes or so. All right. So last week we learned that models like classification models are prediction functions. So if we have at training time, we have 3 columns. At test time, we have 2 columns. Our model is able to regenerate the third via a prediction. Now, we've also I started to hint at the fact that models can differ in their accuracy, right? So if you have the choice of these 2 classification models, nearly everybody would choose the top one as a more accurate model. The green region encompasses more green data points, if you will. But accurate models can also be more or less complex. So both this model in the top left quadrant and this accurate but complex model, they both get about the same number of data points right, roughly, but they vary in their complexity. And we can fill out this quadrant, so we can imagine erroneous complex models. All right, so a question arises, which is we have this intuitive sense of simple versus complex, but how should we go about defining it? All right. So before I attempt to answer that question, I also want to mention that this quadrant idea that I'm pitching also applies to regression. So we can imagine regression models, trend lines that are accurate and simple, that are accurate and complex, that are erroneous yet simple, and erroneous and complex. So this quadrant applies to both kinds of supervised learning. All right, so the question remains, let's define complexity. So in this classification quadrant over here, we might imagine that complexity correlates to the number of layers in a deep learning network. On the right, with the polynomial trend lines, we might imagine that complexity somehow relates to the degree of the polynomial. So recall an 8-degree polynomial has ax to the 8th, right? And that has about 8 curves in it. So we might imagine that these things are how we define complexity. But more generally, let's try and figure out how to generalize these 2 observations. We might imagine complexity as the number of parameters in a model. This is one of the most common ways to approach complexity. But we can also think about the size of these parameters. If we have parameters that are near 0, perhaps they shouldn't count as much as parameters that are very large. Okay, and this is a more sophisticated thought, if you will. Each of these functions, it has a certain amount of squiggles, if you will, or high-frequency spatial information. So we might imagine that the bumpiness in your prediction function is the thing that defines complexity. Okay, so these are 3 definitions. The takeaway I want to impart is all of them kind of get at a piece of the truth, if you will, and there is no like unifying vision as far as I can tell. But these three definitions all hold kind of an aspect of what you want to understand. Okay. All right. So a brief review. So this is what is learning versus predicting. We talked about data and models and how learning is the process of taking data and training a model via these 2 lines in scikit-learn. So in practice, what this means is we have gradient descent, which trains the model parameters, the slope and the y-intercept, such that the resulting function, the line, conforms to your data as closely as possible. And then once we have a model, prediction is simply taking that model and moving back to your data. So you have a data point 0.2, you need to predict a new y value, that's this area right here, and you do that by simply just plugging in that data point into your prediction function. So this is learning versus prediction. Okay, so now what I want to talk about now is how complexity bears on this simple distinction that I've drawn. So we might let's define accuracy as error as measured against your historical data. So if we look at our quadrant, we might imagine that in the top row, the accurate columns, we get low historical error. And on the bottom row, for the erroneous models, we would get high historical error. That's what those orange bars represent. But we might also define generalizability not as the future error itself, but how much worse you do in the future compared to how you're doing in the past. Let's define that as generalizability. And if we actually measure this generalizability error difference in this quadrant, what we'll find is something like this. And what this is telling us is that simplicity correlates with generalizability, that a complex model does not generalize well. That's a big takeaway from this slide. Complex models tend not to generalize well. Okay. But how can we ensure that our models don't become too complex? Recall that when we train, when we take this training data and we construct our model, we know absolutely nothing about our future data in purple here. So at training time, we don't have access to these generalizability measures. And the top left, simple accurate and complex accurate models look extremely similar at training time. So it's a bit of a mystery, or it should leave a bit of a mystery in your mind. How can we choose between simple accurate and complex accurate if at training time we have no access to this generalizability measure? Okay, now what I want to talk about now is a very important idea within machine learning, and one that you'll need to do over and over again in your code in the weeks ahead, and that is the concept of data partitioning. So this is the naive approach where your historical data is known and your future data is novel. And the way that you implement this in scikit-learn is you do something like pandas read CSV, and then you parse from that data frame X and Y, where X is this orange historical data, and Y, and Y is this novel. Oh, I'm sorry. No, X is this top row here. This is your predictors or features, and Y is your bottom row, which is your label. Okay, so this is how you do it in scikit-learn. And then if you're doing it if you're approaching this naively, what you would do is you define a model like linear regression, and then you do .fit. Okay, but what I'm trying to point out is that this is erroneous, that you should throw out these two lines. Okay, and the reason why I'm saying throw out these two lines, that this is a mistake, is we need a way to test generalizability before deployment. Okay, and the key insight is that we need to hide data from ourselves. We need to decouple the known from the historical. We need the past to pretend to be the future. Okay, to do that, we partition, which means we separate our data as follows. We build the wall between these two subsets, and then we only train on this known data on the left. And we treat this historical data as novel on the right. And to do this in scikit-learn, what you do is you do train test split. And that will divide your X and Y into these 4 different sets. And then you want to fit on X train and Y train. So your first takeaway is always write these 2 lines of code. Never write the top line. It's a fairly straightforward takeaway. But as Nathan pointed out, there are more subtle ways in which you need to be aware of this distinction of data partitioning. This wall of bricks, if you will, right here, this can leak in subtle ways. So for example, when you're hyperparameter tuning, when you're fitting and encoding, or you have some research degrees of freedom with regards to feature engineering, you're kind of, this data right here can become compromised. The stuff that your model trains on implicitly leaks. So partition leaking is a sophisticated topic that we're actually going to be exploring in course 2, week 3. But for now, just be aware that this topic is more important than use these 2 lines of code. It's a more general topic. All right. Okay, now, before we dive into our final slide, I wanted to talk about one reason why I find this particular machine learning topic interesting. So let's turn now from machine learning to the theory of science. So it turns out that most scientists tend to endorse a philosophy called falsificationism, which is scientific theory is only worthwhile if it exposes itself to refutation. Everything else is dismissed as not even wrong. Okay. So it turns out that this might not be the most sophisticated way to understand scientific theories. That sometimes scientific theories are wrong, but they get about roughly the same number of predictions correct. So maybe we should move away from falsificationism and more explicitly compare a scientific theory and prediction functions from machine learning. All right, so a concrete example. Ptolemy, with his theory of astronomy, described the planets as revolving around the Earth. This is an Earth-centric solar system, and these epicycles to explain the weirdness in his data. Whereas if you have a Galilean theory, this is heliocentric, and this right. So we now know, of course, that that the sun is the center of the solar system. But back when Galileo was creating his theories, it turns out that both the Ptolemaic theory and the Galilean theory roughly explain the data about the same. So why, if you're living in the time of Galileo, why should you prefer his model versus the Ptolemaic one? Are there any guesses why we should prefer one over the other? Right. The principle that dates back to antiquity is you should don't multiply conceptual entities without necessity. This is called Occam's razor. And the formal term is parsimony, as another word for simplicity. So in science, you appeal to Occam's razor to prefer the Galilean theory. And Occam's razor correlates with the machine learning concept of avoiding overfitting. Okay, so this is just one application. We're going to move back to machine learning after this. Okay, so I've talked about how generalizability matters as much as accuracy, but how in practice do we promote generalizability? This is the concept of regularization. So it turns out you'll only be able to fully understand this in course 2. But it turns out that gradient descent, what it does is it tries to minimize error. So it takes a cost function j and it finds the parameters that minimizes this error function. Okay. But the cost function that we'll learn about only penalizes bias. It only pushes us up in this quadrant. We need to also penalize complexity. And the way that you do this, the insight that regularization provides, is if you modify this cost function j to include, to not only encode your error, but also how big your parameters are, then you can, once you modify your cost function, then your models tend to select the top left quadrant. Your gradient descent finally decides, I like simple accurate more than complex accurate. Question?
What do the symbols around E and theta mean in the J equals line?
Oh, yeah. So at this J line here, we'll get into this more in course 2. You don't need to know this now. But what these symbols mean is we're treating each error, we're putting them in a vector, and then these double bars represent the vector length, or what's called the norm. So this is the sum total, if you will, of the errors plus the sum total of the parameters. So that's what that means. And ignore the 2. We'll explain that later. Other questions? All right. Okay, finally, this is our application slide. So if you do a regularization in practice, what you'll find is without regularization, you get a complex classification function. This was a programming assignment in the deep learning course. But once you apply regularization, you'll see that your boundary starts to smooth out. So this is a model with regularization. It has low complexity and high generalizability. And this is another form of regularization, more sophisticated form, and that's the same takeaway. If you apply regularization, you get a smoother curve, you get a more generalizable function. All right, that's all I had.